we're going to start talking about something called relations. And actually, a relation is a fairly simple concept that we're going to look at. And it simplifies a lot of things. Let me ask you this. Everybody in here has had calculus, right? And what do you do in calculus? You take these things called functions and you do fancy stuff with them. You take a derivative, you integrate them like that. What is a function? Like, give me an example. Just say from R to R.
But there's all an operation on one more.
Okay, so you're talking about a function of maybe more than one variable, right? What's the rule? So it's an operation on it. I find this is true that, you get this, you hear these kind of definitions. How many of you have heard this one? A function's like a black box. You put in a value for X and it spits out a unique value for Y. And usually you hear that word unique and sometimes it's glossed over a little bit. Part of what we're going to do is we're going to see actually functions defined properly from relations later on. And to me, it makes more sense. It doesn't really make sense to teach somebody in pre-calculus about relations. Probably that's probably a lost cause and a hill I'm not down. But we will see here that from a relations point of view, we will see the functions much clearer. So the first thing that we need to do is I'm going to start off with a kind of set that you can build from existing sets. And this is something that you have seen. This is where you've done some calculus, Calc 2 and Calc 3. This is the set of ordered pairs A, B. And we usually think of this as the plane, don't we? The first coordinate is the X coordinate, and the second coordinate is the Y coordinate, and this tells you where everything is, right? This is an example of what we call a Cartesian product. Definition. Let A1, A2, AN be sets. So this is just some collection of sets. We define the Cartesian product. What is this Cartesian product? It is, here's another outline. Well, this is exactly, I hope what you would think it would be. This is the set of n equals. So you've got n sets, you basically got n coordinates. First coordinate comes out A1, the second coordinate comes out A2, and so forth and so on, right? This is what a Cartesian product is. And n A1 cross A2 cross n, we say A1, A2, AN is equal to X1, X2, Xn, if and only if AI equals Xi. Wrong. So in other words, two n tuples are equal if and only if all their coordinates match. Right? I think that's what you would want that to be as far as equality goes. So what happens if one of these sets is empty, any one of them? Or more? What can you say about this? Well, what does an element look like here? Right? It has to be in coordinates, and each coordinate has to come out of one of these sets. How many elements are in the empty set? Nothing in the empty set. There's nothing you can put in the ith coordinate, so this is the empty set. Right, okay. Number two. Let's say that each AI has mi elements in it. So A1 has M1 elements, A2 has M2. How many elements do you suppose are in that? Well, think about it this way. How do you build an element in here? You have to choose coordinates, right? How many coordinates are there? They're in coordinates, right? So this is like that thing last time when we did counting. Remember how, oh, if you have this many ways to do the first task and this many ways to do the second task, then you multiply them together to get the entire task, right? How many ways are there? Pick out a coordinate for A1. M1 ways. For A2, M2 ways. M3, all the way up to. So the number of elements in the Cartesian product is the product of what's in separate sets. Are you okay with that? Okay. So A. Probably. How many elements should there be? Guess there should be 12, right? One W, one X, one Y, one Z, and then repeat through the other numbers. And you can go crazy with this. You could, for example, you might look at what is A cross A. There are four things, I'm sorry, there should be 9 of these, right? One of my favorite sets, right? There will be a lot here. I guess 64 times 9, right? So 576 or something. Anyway, this will be a lot of things in here, right? Right. So, any questions on how to form these Cartesian products? Okay, so let's look at a theorem. As you might guess, so we've got this new kind of set. So we've got a tool. build new sets from old. If I've got two sets here, I can build a Cartesian product. I can even use the set over and over again, sort of redundantly, and build bigger ones. Right? I mean, after all, didn't we build the plane from R goes to R cross R, that's plane, R cross R cross R is space. There. Let's see how these play with our other operations on sets. Like intersection, union, and such. So. Number one, well, so says. Number one, A cross B union C is A cross B union A cross C. Two. Intersection works the same. When you cross A with B intersect C, it's A cross B intersect A cross C. Three. If you look at A cross the empty set, you get the empty set, and we pointed that out too. Notice that if you believe my formula for the number of elements in it, this should be the number of elements in A times number of elements in the empty set, which is 0, right? So that kind of makes sense. A cross B intersects C cross D. Equal A intersects C cross B intersect B. And 5, A cross B union C cross D. Um, let's take a look at that. Let's see what the difference is. Improve some of these. By the way, how do I show the two sets are equal? We need to show containment in both directions, right? Especially since we're doing this whole Cartesian bit. So let's look at one. Let's do this containment. Suppose that we have something in okay, so I need to write this in its proper form. Suppose X is an element in A cross B union C. What does this mean? This means that X equals A Z, where A lives where? A lives in A for sure, because it's the first coordinate, right? And what about Z? Where does it live? It lives in B or C. Everybody okay with that? Let me point out if Z is in B, then X is in A cross B. So I know that Z is in one of these two. If Z happens to be in B, then this thing is in A cross B, right? And if Z is in C, then Z then X is in A cross C. So X is either in A cross B or X is in A cross C. So there's one container. How about the other? For the second part of the containment, now suppose X is in A cross B union A cross C. So I know, what do I know about X? Well, it's in one of these two. So in particular, I can write X in the form as A Z, where A Z is in A cross B, or A Z is in A cross C. So we conclude immediately A is in A. Right, because no matter what, that first coordinate has to be an A. Great. Okay with that. And Z is in B or Z is in C. Right? Because the second coordinate either lives in B or it lives in C. One of the two. Hence, uh, because the first coordinate is an A and the second is in B or C. Everybody, okay with me? Any questions? Okay. Try to do the second and third one. I want to go through 4 and 5 more carefully because you'll find this a little bit puzzling. That you get equals here, but you only get containment here. Right. Let's see if we can kind of figure out why that's the case. Let's look at 4. Again, to show equality, I need to show containment both ways. By the way, 5 should be easier, right? Because I only have to show this side is containing this one. I don't have to do the other one. But I do want to try to figure out why the other one didn't improve. Let's see if this sheds any light. This will let X A cross B intersect. So what does this mean? Well, this means that X is equal to ST, and this is an A cross B, and you repair ST is in C cross T. Right? So let's look at the first coordinate. It has to be in A, and it has to be in B. Do I agree with that? The same business is going on with the second coordinate, right? There's no difference here. Also, T is in B, and P is in D. So P is in B intersect D. Right? So ST, which is X, is actually in A intersect C cross B intersect. Everybody okay with that? Let's go the other way. How about the other way? Well, now. Let this live in A intersect C. Okay. What does this mean about S? So S is actually in A, right, S is in A and S is in C. P is in B and so what does this mean? So if you look at the order pair ST, this is in A cross B. Because S is in A and T is in B, right? And ST is in C cross D. Because S is in C and T is in D. So this is A cross B intersection. So these two things are equal because the left is contained in the right and the right is contained. Yes.
People say that A, like ST is an element of A plus E two or no?
What's E?
Or like ST is an element of A cross D, or could you only say A cross?
She's right, right? Look at ST. Isn't it in, it's in A and D. So you're right. It's also in, for example, A cross D.
So it's just because we're trying to prove that.
Exactly. That's exactly right. You could do some, so that's a good observation. You could do some messing around with it, right? This is also in A cross D. How about this one? I'd really like to get to the bottom of the mystery why this is only contained one direction. Let's do 5 here. We're going, yes.
I was just wondering if that means A, B, C, and D are commutative.
No, the order, so. These are not the same set in general, because I'm paying attention to the order of the coordinates, right? They're the same size and they're very similar because the coordinates are reversed. They're not the same set. So let's let X A union B cross C union D. Let's suppose that's what's here. Oh, well, Started in the wrong place, haven't I? It's A cross B. But X, B, and A cross B. C cross C. There we go. Well, what does this mean? It's an ordered pair, so X equal to ST. And what can I say about ST? ST is in A cross B, or ST is in C cross B. Okay, so far with the assessment that we've done. Okay, so how do I move forward from here?
She's not here either.
Well, so look at the first coordinate. The first coordinate S is in A or it's in C.
Yeah.
I agree with this. So that the first coordinate S is in A or S is in B. I'm sorry, C. I agree. And the second coordinate I agree with that. So when I look at ST, if it's in here, then the first coordinate's in A, and if it's in here, the first coordinate's in C. Look at the second. If ST is in here, then T is in B. If it's here, then it's in D. So notice that my conclusion here is that S is in A union B, I'm sorry, A union C. Wait. And T is in B union B. Hence, X, which is ST, is in somebody explain why, so we proved this. Why doesn't this hold? Why didn't it work the other way? Yes.
Because ST could, if it's in A union C cross B union D, could be in, like C cross B.
Right. The problem is you can mix and match coordinates too freely, right? So I'm gonna leave that as an exercise. So see if you can figure out, see if you can find an example. You should be able to do it with pretty small sets here. See if you can find an example in general where you have something that's here, but you can't write it in one of these 2 points. It's an order variable, A comma B or C. Okay, questions? Now that we've kind of warmed up here and we've got some of these basic properties of how Cartesian products play with unions and intersections, I can tell you what a relation is. This is a fundamental concept, and we're going to do a lot with relations. Functions or special cases of relations. Any of you ever heard of equivalence relations? Ooh, that's a big one, Matt. It mimics equality, and I know you're fond of talking modular arithmetic. This is an equivalence relation. It's going to be very, very important. People that do number theory coding, things like that, they really like equivalence relations. So there's order in relations. That's another big one in math. What do we try to do in math? Oftentimes is we try to put things in an order. This is big, this is smaller, right? So these are all kind of special cases, very important application, special cases, what we're talking about. And the definition is incredibly simple. And it's so general that this is why we specialize in things like equivalence relations, order relations, functions. But definition. 314. Let A and B be sets. A relation, R from A to B. So sometimes we say relation R from the set A to the set B, or it's a way relation relates to set that, A to B. Here's what it is. Very simple. That's it. A relation from the set A to the set B, any subset of A cross B you want is a relation. It could be the empty set, it could be all of A cross B, whatever you like. So, if the order pair A, B is in R, we sometimes write A, R, B. And this means that A, B is in the relation R. Remember what R is, it's a subset of A cross B. And sometimes when we use this notation, we'll say that A is related to B in this relation. So sometimes we'll say A is related to B, means the order pairs in here. If the A can, we say R is a relation on A. So it's a relation of the set A to itself. Right. So it's a subset of A cross A. So let me give you an example here. Okay. Here's a relation. Let's go. 1 triangle, 2 star, 3 circle. This is a relation from A to B. What is it? It's a freaking subset of A cross B. That's all it is. That's all it is. And anything I can make up is another relation. This one actually is a function. You can think of it that way, right? 1 goes to triangle, 2 goes to star, 3 goes to circle. Y'all remember that old definition of function from the calculus days? It's a black box. you input something and it gives you out a unique something. This particular relation is a function. Here's one that's not. One triangle. One star. Two circle. Three square. Square. And let's see if I covered everything. So from your calculus stage, can you tell, this is another relation, it's a subset of A cross B. Everybody agree with that? Can you tell me, why this isn't a function? Does anybody remember the old? One has two outputs, and actually so does two, so this isn't a function. So relations are actually gonna give us an easy way to kind of witness them until it's a function. Here's another example of relation. While we're on even calculus, let's let A be real numbers. So I'm going to consider the following subset of R cross R. It's all ordered pairs that look like this. This is a relation on the set R cross R. You can actually draw a picture of this one, right? Because what does R cross R look like? It looks like a plane. And these are all, this is a subset of R cross R, right? Because R's, X is a real number, sin X is a real number. What does this subset look like? You can actually draw this one. So functions, as it turns out, although we haven't gotten to it yet, is a special case of relations. Here's another one. Here's another good example. I'm gonna do a number of these here. Now, I'm gonna give you a relation on the set C. We declare N related to M. And remember what that means. That means N M is in our subset. If and only if N minus M is even. So my subsets, my subset of Z cross Z, can somebody describe what the coordinates look like?
Uh, 3, 1, 4, 4, 2.
Okay. What does it mean to have membership in here? The difference in the coordinates always has to be even. So that means that the coordinates either have to both be even or both be odd. Right? So this particular subset of Z, this particular relation gives you just all ordered pairs that are either both even or both odd. This is actually going to be important. This is in fact an equivalence relation, which we'll get to later. I love this.
Question about that format, or how do you write that? Like, would it be like capital A or lowercase a R D?
Well, when I use the lowercase, I usually refer to the elements within the set.
Oh,
And the uppercase refers to the set itself, where
Okay.
I'm pulling things from.
So it's a relation of the elements, not of.
No, it's a subset of A cross B, and what you want to know is what elements, what ordered pairs are in the subset, right? This is Z cross Z, and both even, both odd. That's the rule for living in that particular relation that I gave here. So, example. What I mean, the set of people with English first name. And I don't really mean English, I just mean it starts with one of the 26 letters in the alphabet, right? So you can pick an English name if you like. I am going to declare, we're going to say so again, this is a relation on the set E, right? We say that for persons A and B, A is related to B if A and B have names beginning with same letter. It's a relation, it's a subset of all people, people cross people. And I say that, two people are related, that is the ordered pair of person one, person two. Related if their name begins with the same letter. By the way, if there's at least one person in my set of people, and I know there's at least one person that has names starting with the English letter, me, right? Okay, so there's at least one person in there. Is it possible for this to be empty? You got me there, but actually you only need one person for this not to be empty. Why? Because unless you're schizophrenic, your name only begins with one letter, right? Jim is related to Jim, right? And so that's one thing that's true in this particular relationship is anybody's related to themselves, right? So you might think you're lonely, but you've at least got yourself, right? A is related to A. Any person related to themselves. But what does this do? What do these ordered pairs do? They clump together all the people. So I'm in the J club, right? All the people join my club. I'm in an ordered pair with them if their name begins with the J. And what else is true about this? Suppose A and B are related, so they both of their names begin with the same letter. What else is true? It's almost so silly you might not see it. This was reversible, right? The ordered pair. Also, what else is true? Suppose these two people have a name that begins with the same letter, and so do these two. What can we conclude from this? These two have the same letter beginning of their name, and so do these two, then A and C have the same first letter in their name. Great. This is actually, these three properties, everybody's related to themselves. If two people are related, then they're reverse related, and transitivity. This is a very important type of equivalence relation called an equivalence relation, which we will look more in depth at later. You could also say two people are related if they happen to have the same zip code, right? Or if they happen to have the same three-digit area code on their phone number, for example. Here's some other examples. Yeah. This really should be my definition. As definition. Set of example, 319. Yeah. A is not an empty set. Then there's a relation on itself that is very convenient. It's called take any set. Notice you're just kind of mimicking A here. You just, whatever you see in the first quarter, put over here. This is why it's called the identity relation. Basically, you just repeat all the things of A as an ordered pair, right? This will come up as well. The identity relation is a very important relation. And let me give you a couple other definitions while we're deconstructing this here. Let's have a relation here. Let's say that R is relation from A to B. Keep it simple. That just means it's a subset of A cross B. Then domain of R. This is actually a subset of A. This is all crap in A such that the order pair AB is in R for some B. So remember what the domain is this. A relation is a subset of A cross B. So it's just a whole bunch of ordered pairs, A cross B. What's the domain? If you can find it in one of the left coordinates, if this is one of the left coordinates, it's in the domain. What do you suppose the range is? If you can find one of the other coordinates, it's the range. Set B and B such that A, B is in R for some A, A. And do you all remember doing inverse functions? When you probably in pre-calc, you did the inverse trig functions. Wasn't that a bit of a pain in the butt? Inverse relations, so much easier. They are so much easier, and they will help us do inverse functions in an easier way too. So final definition of the day. Let's let R relation from A to B. So what do we got? This is a bunch of ordered pairs, A comma B, some subset of A cross B, then the inverse of R. Oh, I love this. I love this. I love this. This is just BA such that AB is in R. What is the inverse of a relation? Take everything in the original relation and turn it around. That's it. You gotta love simplicity. Any questions? All right. Well, you all have a good one, and we will see you next time.